All right, Physics 1, welcome back to part 2 of the lecture. Sorry for the quick cutoff. I had a coughing fit. Okay, so we had been talking last time about the exciting a mercury atom using an electron with a kinetic energy of 6 eV. So it's going to deposit 4.9 eV of its kinetic energy into the mercury atom and move along with 1.1 eV. And if you wanted to keep the mercury excited, you'd need to keep bombarding it with electrons to excite it, as atoms want to de-excite, and they're going to do that by releasing a little bit of light. Now, going off of this example, what would happen if you send a bunch of electrons in to Hg, or mercury vapor, with a kinetic energy of 4 eV? Nothing interesting, actually. There's simply not enough kinetic energy to excite it. So in order for a particle, or for collision excitation, it needs to have at least enough kinetic energy to excite to one of the energy states. By the way, this example here of you looking at mercury excitation through collision is how they determined the energy levels of mercury. So what they did, so in the mercury experiment, they sent in an electron beam with a kinetic energy of 9.8 eV. And what they found is there was enough energy for each electron to excite 2 Hg atoms. So exactly what energy is needed, like I said before, varies from atom to atom, but all atoms have these discrete energy levels, and you can see the energy levels through something called emission and absorption spectra. So, energy levels, and perhaps you talked about this in a chemistry class, either in high school or in college, can be determined through emission and absorption spectra. All right, so let's do some more examples. An electron with kinetic energy 12.9 eV collides with a hydrogen atom in ground. So that would be the n=1 state. After collision, the hydrogen atom is in the second excited state. So that would be n=3. So I'm giving you these in the lecture. On a quiz or an exam, I'd expect you to know this. So what is the kinetic energy of the electron after collision? So we know it deposited some of its kinetic energy into the hydrogen atom. We want to know how much is left over. So our system is going to be the electron and the hydrogen atom. That way we have nothing in the surroundings. So once again, we're going to set up our energy principle. So when in doubt in these chapters, always start with the energy principle. So we end with an excited hydrogen atom and the electron with some final kinetic energy, and this must be equal via conservation of energy to the initial energy of the hydrogen plus the initial kinetic energy of the electron. All right, plugging in our known numbers, we have minus 13.6 eV over 3 squared, because it's in the n equals 3 state at the end, plus the kinetic energy of the electron final, which we don't know yet, and this is equal to minus 13.6 eV over 1 squared plus 12.9 eV, the original kinetic energy of the electron. So then we just do a little algebra, and we see the final kinetic energy is 0.811 eV. All right, so question. Could this electron have excited to the third excited state? So the n equals 4 state. And the answer to this, pretty easy. So delta E between the ground and the third excited state, so 13.6 eV over 4 squared minus 13.6 eV over 1 squared. This is equal to 12.75 eV, which let me show that to you. And if we remember, the original kinetic energy is 12.9 eV, so this would have been no problem. What about n equals 5? Delta E for that would be 13.06, so nope. So this electron could have deposited enough kinetic energy to go into the first, second, or third excited state, but it would not have been able to excite up to the fourth excited state. All right, so moving along. So we know that atoms can gain energy through photon absorption, and atoms can lose energy by photon emission. And these, for any given atom, for any element, correspond to very specific energy levels. So these are also quantized packets. So these emissions are in quantized energy packets, a little quantized bit of energy. That's what a photon is. So what this looks like is you start off with your excited hydrogen, and then it goes to a unexcited hydrogen plus the photon. Now, of course, it could go down in different levels as well. So it could go from the fourth excited state directly to ground, but it could also de-excite fourth, third, first, second, ground. All right. And in terms of the energy principle, so you'd have the energy of the hydrogen final plus the kinetic energy of the photon, and this would be equal to the initial energy of the excited hydrogen atom. So once again, we're seeing a real similar setup. So let's go right into an example. So different atoms have different energy levels. We're going to consider a fictitious atom. So let's consider a fictional atom with a first excited state of 7 eV above ground, and the second excited state is 9.2 eV above ground. What is the energy of an emitted photon? Photon when it drops from the second to the first excited states. All right, so once again, we'll set the system up to be all particles. The surrounding will be nothing. So we have E final is equal to E initial. So we'd have the first excited state would be whatever the ground is, plus 7.0 eV, plus the kinetic energy of the photon, because in the final state, the photon energy has been released from the atom. This will be equal to E naught plus 8.5. We don't know what ground state is, and we don't need to. 8.5 eV. Okay, so we see that this is on both sides, and the kinetic energy of the photon emitted would be 2.2 eV. So that's just how we play this game. Very similar to what we've been doing so far. All right, so moving on. Sticking with the idea of excited states and photon emission. So excited states, as I've said before, have limited lifetimes. So they want to decay, and they're going to decay by emitting photons. So atoms want to go to ground. How long they will stay excited depends on the particular element. So the wavelengths emitted, the wavelengths or energies will correspond to quantized energy drops. So they can only emit particular wavelengths. I know I keep repeating this, but it's just really important to help internalize this idea. And these transitions are called quantum leaps. So it's not just a bad television show from the 90s. Or maybe you liked that show, I don't know. I do know somebody that was an extra on the show Quantum Leaps. Okay, so like all things quantum, you actually can't calculate precisely the time that an atom is going to de-excite. You can only calculate the probability. So precise time unknown. Uncalculatable is more accurate. Only probability. So we know about when it should probabilistically de-excite, but you cannot predict the individual de-excitation. You can only model the behavior of groups. So the probability can be described using e to the minus t over tau. So t is the time in seconds, generally in seconds, and tau is the lifetime. And the lifetime is determined typically by measurement, experimentation. So when tau is equal to t, the probability is e to the minus 1, which is 1 over e, which is 0.368. Or you can think about that as there's a 36.8% probability that it is still excited. So, and we can go after tau through measurement. It can be predicted using quantum mechanics, but the exact emission time is not calculatable. And basically what they do to make these measurements is you look at the emissions of a vast quantity of atoms. So in my thesis experiment, I looked at argon scintillation. So I was exciting argon atoms, and I measured the lifetime of hundreds upon thousands upon millions of excited argon atoms and how long they stayed in their excited state. So this is a doable measurement. All right, so moving on to another example. Let's consider a collection of hydrogen atoms. Initially, each atom is in one of the three lowest states. So we have n equals 1, which is the ground state. N equals 2, first excited. And n equals 3, which is the second excited state. And so the question is, what photons could be emitted from these hydrogen atoms? So what photons? So they're only in 3 different states. Okay. So let's count up the number of states first, or the number of photons first. So we have n equals 3. So the third excited state, you could go from 3 to 2, 3 to 1, and then if you go 3 to 2, then you also go 2 to 1. And then for n equals 2, you've got 2 to 1, and for n equals 1, no emission. You're already in ground, you can't go any further. So we can see that we'd have a photon corresponding from 3 to 2, 3 to 1, and 2 to 1. So there'd be 3 photon energies possible. Also, this would correspond to 3 different wavelengths of light. Okay, so now that we know that there's 3 possible, let's go ahead and calculate them. I'm going to do that actually on a fresh sheet of paper. So we have n equals 3 to n equals 2. This would be minus 13.6 eV. Over 3 squared minus 13.6 EV over 2 squared is equal to 1.9 EV. Then we'd have n equals 2 to n equals 1 minus 13.6 EV over 2 squared minus 13.6 EV over 1 squared is equal to 10.2 EV. And then lastly, we'd have the n equals 3, the big jump, to n equals 1, again, minus 13.6 EV over 3 squared to minus 13.6 EV over 1 squared, 12.1 EV. So these would be the 3 different photon energies available. So in terms of a picture, this is how we would draw this. So here's minus 13.6 EV here, minus 3.4 EV, minus 1.5 EV. So we could go directly from here all the way down to here. This would be via that 12.1 EV emission. So this would be a 3 to 1. You could also go via 3 to 2. So that would be that 1.9 EV. And then we have our 2 to 1, which is the 10.2 EV. So here we have an energy level diagram. Perhaps some of you have seen these before. And so all we're showing is only K plus U energy levels are shown. You don't draw energy levels that aren't possible. Okay, so what you can see is this is very different than a classical system where you'd have a smooth transition down and it would have all of these different available energy levels. Like we toss the ball, it can just go down smoothly, but instead the electron is here, or it's here, or it's here. And it just automatically, it just evaporates. Well, evaporate's the wrong word. Just kind of goes from one to the other. No transition. It's here and then it's here, just like in a cartoon. Okay. And the exact timing of these jumps, as I've said before, is determined through probabilities. We cannot calculate it directly. All right, so for practice, so move on to how many different photon energies would be emitted from atoms in the lowest 4 states. All right, we're not going to calculate the energies, but essentially if you had 4, you could go from 4 to 3, 4 to 2, 4 to 1, and then 3 to 2, 3 to 1, and then 2, 2 to 1. So you'd have 6 energies possible for de-exciting from the first 4 states. All right, so you see how to play the game, and then of course you could just calculate these if you wanted to on your own. If it's something you need practice with, I highly recommend doing it. All right, so let's look at emission spectra. All right, so what this is here, this de-excitation, these photon energies, these wavelengths of light, this is the emission spectra. These are the wavelengths of light that atom is capable of producing. So we can take advantage of this to learn about materials. So suppose we excite a tube of gas using an electron beam. The atoms get excited and then de-excite by photon emission of particular wavelengths. So this is the emission spectra, and we can measure it. So the lines of emitted light are called spectral lines. And that would correspond to the spacing in between energy levels, just like what we saw up here. And that is how, so if we know the emission spectra of a particular type of material, we can use that to determine the composition of unknown objects. That's how we've learned about what the composition of stars is. We have looked at their emission spectra. All right, so moving on. So all elements have emission spectra. They also have something called an absorption spectra. So let's go after how to think about that. So if a gas has every atom in ground, could we observe an emission spectra? So let's think about that. So emission spectra requires atoms to be in their excited state. So no, we could not. It would just be all black. Very boring. All atoms are in ground. Nothing is excited to release any photons. However, we could still learn something about this. We could shine a beam of white light. Now, the reason we would do white light is because it's made up of all the different colors and energies. So it's a continuous spectra. And see what gets absorbed. Because we know that those atoms will absorb particular energies of light corresponding to the energy, their energy levels. They're allowed quantum discrete energy levels. So only specific energies of light. Which would correspond to energy levels. And this would allow us to determine what this gas is made of. So what we could do is we could just look for the gaps. So we could measure light on the other side and look for the missing energies. So this is called the absorption spectra. And then if you wanted to, so you could actually confirm it twice. So if you had your gas and it was all in ground, and then you excited it and you measured which wavelengths of light got absorbed, then what you could do is you could let them de-excite by photon emission, and you could measure the wavelengths of light that got emitted, and you could really confirm what the material is made of. So, thinking about looking at both emission and absorption spectra, why might a gas have 3 lines in the emission spectra but only 2 in the absorption? So remember, absorption starts in ground. So you might have 3 to 2, 3 to 1, and 2 to 1 for emission. And then since it's starting in ground, you would just absorb to go from 2 to 1 and 3 to 1. So these would be the only 2 you would see for absorption. Because in order to see this requires something is already excited to see that absorption line. Okay, so moving along, there's a kind of cool implication about emission and absorption spectra. So why is hydrogen gas transparent? Because we've got hydrogen around us right now. And so the energy required for the first excited state is 10.2 eV. And remember, we only see light from 1.8 eV to 3.1 eV. So we actually can't see those wavelengths of light with our own eyes. That also means that visible light, not only can we not see it, but visible light is not absorbed by hydrogen. So you see, all you need to do to become invisible is you just need to think about which wavelengths of light you're absorbing or not absorbing. Invisible to the human eye, that is. All right, so let's do an example. This is a rather large example, so I'm going to do a fresh sheet of paper. So let's look at determining the energy levels from photon energies. Okay, so you observe photon emissions from quantum objects known to have 4 quantized energy levels. So these have been excited using an electron beam. Emissions are detected with a detector sensitive to the energy range 2.5 eV to 30 eV. So this is the only energy of light, or energies of light, you are allowed to detect. You observe 3 eV, 6 eV, 8 eV, and 9 eV, and no other energies. Okay, so let's say the ground state is minus 10 eV. What are 2 possible energy arrangements? Okay, so we know that we're seeing, I'm going to do a fresh sheet of paper. So we know that we see 3 eV, 6 eV, 8 eV, and 9 eV. Okay, so let's look at 2 possible arrangements. So we could have, we know it goes down to 10. We could say we go from -1 to -2. And then a -4 eV. So then this gets us a 1 eV, which we can't observe. Then we'd have a 2 eV, which we also can't observe. A 3 eV, which we did. A 6 eV, which we observed. This would get us our 8 eV, which we observed, and then a 9 eV, which we observed. All right, so that's one possible. I'll do that again here so we can just see that. So obviously you have to think about the fact you cannot observe an energy level lower than 2.5 eV, so that could exist and you could simply not see it. So you always need to know the limitations of your instrument. So let's look at another arrangement. Once again, starting at -10, go -10, -9, -7, and -1. Okay, so let's see what emissions that would get us. So from here to here, you'd have a 1 eV, which we can't observe, a 3 eV, which we did. Check that off. The 9 eV, which we observed, a 2 eV, which we cannot. We'd have an 8 eV, which we could not observe, or which we did observe, and then a 6 eV here, which we also observed. So either one of these two energy arrangements could correspond to the energy levels. So remember, in this class, what we're looking at is just setting up the premise for energy levels. There is more involved in terms of what's likely and what's allowed. But for now, just looking at pure emission spectra, this would be two possible ways. Okay, so we've seen this. Now let's move on. Let's say we obtain a second detector. So you obtain a second detector sensitive to photon energies from 0.1 eV to 2.5 eV, because we suspect there's some things we're not seeing. What would you observe? Well, we already know the answer. And this would be true for both. You would observe 1 eV and 2 eV. Okay, so next, so you've excited it. So next, you turn off the electron beam and let it go to ground. So everything is unexcited now. You shine white light, so that continuous spectrum, and look at the absorption. How could this help you? So let's think about this. So the first option, option 1, you would see 6 eV, 8 eV, and 9 eV. And for option 2, you would see 1 eV, 3 eV, and 9 eV. So now you're seeing which ones get absorbed. So you remember, ground is off the table, so you're looking for here to here, 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 and here to here. So, and emission and absorption. Help determine composition. Okay, so just a couple final thoughts on this section of Chapter 8. So we have been using some simplifying assumptions, which I've alluded to. So we've been assuming that photon emission can occur from any discrete level to a lower level. Reality, some transitions are forbidden. And this has to do with the conservation of angular momentum. And again, you want to start getting into that. Physics 3. And we have been ignoring probabilities. And that's because it's beyond the scope of this chapter. This chapter is just laying down the groundwork so we can have a nice, fun foundation to build upon. All right, so this wraps up part 2 of Monday's lecture.